As a former mobile developer myself, I've been following Russell's work quite closely, and I think you are all going to be very excited by what you see. Please make welcome Russell Keith-Magee.
Well, thank you very much, Chris. As you said, my name is Russell Keith-Magee. I'd like to welcome the captioners to the semi-finals of the World Speed Transcription Championships. If you have heard of me before, and it's not because of my reputation amongst the reputation of fear amongst captioners, it's probably because of my work on the Django project. I've been a core team member on Django for almost 11 years, and I was president of the DSF from 2011 to the end of 2015. Django's been around for just short of 11 years, and Django and the web are still very important platforms. They're not going anywhere in a hurry. But over those last 11 years, we've seen the emergence of a new type of platform, the mobile platform. Delivery of web content for a mobile form factor is one approach for this, and it's something that has evolved over time as best practice. But mobile platforms also deliver a different way to deliver content as native applications. Now, it's no secret the mobile device space is dominated by two major players, Android and iOS. But unfortunately, Python hasn't historically had a really good story for either Android or iOS. If you wanted to write applications, mobile applications for iOS, you either had to learn Objective-C or more recently Swift, and then to write your companion Android app, you had to learn Java and a completely different set of APIs for Android. Now, there are a couple of other options that are out there for using other languages, C#, JavaScript, even Ruby, for varying degrees of cross-platform and native. But Python was, for the most part, absent. It wasn't completely absent. Kivy has been working in this space for a couple of years. But those tools were very much wrapped up in the Kivy toolchain, rather than being something generic that you could use without Kivy. Over the last 2 years or so, I've been working to rectify this situation. And the purpose of this talk is to show you what's currently possible and give you a dive into how some of the pieces work to deliver a Python on mobile experience. Now, the first thing that I want to address is exactly what I mean when I say mobile Python. Other people may and do have very different interpretations of this, and they're all completely valid. But I have a very specific definition which rules out certain options. When I say mobile Python, I'm talking about the development of a native application delivered as a native application using native system APIs. Let's break that apart. I'm talking about native applications. I'm not talking about HTML5 apps that are delivered using Python. I'm not talking about a native shim that displays a web canvas that then renders content generated by a client-side web browser. I'm talking about an app that you start the same way you start any other app on your device that behaves the same way as a natively developed app behaves. I'm also talking about apps that are delivered using the normal platform mechanism, downloadable as a single bundle from an official app store. Now, I know you can jailbreak devices, and those approaches open up all sorts of options, but any ecosystem that relies on jailbreaking won't ever really make it to the mainstream. You can also do some really nifty things with system services on Android and treat the Android platform as a low-power Unix server. That's not what I'm targeting. It's a very interesting approach, but it's not what I'm targeting. I'm talking about developing and deploying apps with the potential for mainstream adoption. Essentially, the end user should not know or care that the app they're using was written in Python, any more than the users of Instagram and Disqus care that the website was written using Django. If they need to know or care, then in my opinion, you've failed. Lastly, the apps use native system APIs. The apps should look like native apps, feel like native apps, and provide access to any native service the platform provides. Using Python shouldn't be a constraint on your options in terms of what you can achieve. Okay, so given that definition of mobile Python, what is currently possible? Well, the TLDR version is you can write a native iOS application, you can write a native Android application, and you can write a cross-platform application. Okay, so let's have a look at those. Start with iOS. We're going to start with iOS because it's actually the easier of the two. It's easier because the toolchain that you use to develop native iOS apps is Clang, the same C compiler that you use to compile CPython on a Mac. Now, this doesn't mean that iOS is just a POSIX. It isn't quite that simple, but it's pretty close. close enough that with a few patches and disabling a couple of modules in the standard library, you can compile CPython 3.4 or 3.5 sources so that they will run on the iOS simulator or on an ARM v6, ARM v7, ARM v7s, or ARM64 processor, which covers pretty much every iOS device that's been sold over the last 5 years. A patch to do just this has been submitted for inclusion in the CPython itself. It's issue 23670 on Roundup, the bug tracker, Python bug tracker. There are some design decisions that need to be ratified. There's an issue with the build system that was introduced in CPython 3.5 that needs to be addressed. But ultimately, merging this patch is really waiting on attention from a champion within the core team. If that was done, iOS could be a fully fledged platform supported by CPython. Now, I did talk about this at the Language Summit on Saturday, and there are some other concerns that exist. That's going to be an ongoing discussion for some time. But you can build it outside of being in the official tree. Okay, so how does it work in practice? You don't have a command line in which you can type Python -m myapp. So how do you use CPython on iOS? Well, you treat it as an embedded application. You write a very small C stub with a mainline C file that starts the CPython interpreter as an embedded library. And that starts the iOS, and then start the iOS event loop. Now, I could dig through all this in detail, but honestly, there's really no point. Firstly, because it's pretty much a vanilla usage of the embedded CPython API, which the CPython docs actually do really well. But also because it's frankly just easier to template it. Python iOS template is a cookie cutter pattern that you can use to generate an entire ready-to-run iOS project. You run Cookie Coder over that template, download the precompiled iOS libraries, drop them into the project, full instructions on the GitHub page that's linked there, and you're off to the races with a fully functioning Python instance that's running on iOS. So, once you've got that stub project, you'll actually want to do something. You could start by writing your standard hello world, but that's not going to be very enlightening because it's going to just output to standard out, which you can see if you're plugged into Xcode, but it isn't visible on a standalone iOS device. What you really want to do is invoke some native iOS APIs. So how do you do that? Well, iOS native libraries are provided in Objective-C, which is a quirky language, but the good news is that it's actually really compatible with Python. Quick aside, Apple threw a little bit of a spanner in the works a couple of years ago with the announcement of a new language called Swift. The good news is that this doesn't appear to be changing anything from Python's perspective. Swift does look really interesting, but to my read, it's ultimately just a nice set of syntactic sugars and some type safety around the Objective-C runtime, replacing the quirks in Objective-C syntax with some dynamic conventions that would be familiar to you as a Python developer. There also aren't any signs that Objective-C is going away, and even if it did, Swift is built on top of the same Clang toolchain, so there will almost certainly be a way in. It's just a question of what that way is. Okay, so back to Objective-C. Here's some sample Objective-C code. If you've never seen Objective-C before, it's just lots of line noise. But what it's doing is constructing a new NS URL object, the Objective-C representation of a URL. What we're saying is we want to pass the URL with string message, the string http://pyb.org to the NSURL constructor and get back an NSURL object. Okay, so how do we do that in Python? Well, the thing is, Objective-C is designed as a really thin syntactic wrapper over raw C. The quirky Objective-C syntax is literally a translation to raw C API calls. So let's just roll this out a little bit more. We'll replace the at syntax of at http://pyb.org with a slightly more lower level API. So what we're going to do here is allocate a string, NSString alloc, pass it a message in it with characters http://pyb.org. That there is not an Objective-C string, that is a raw C string of length 16. That will give us a Objective-C NS string, which we can then pass into our constructor. That series of calls can be translated into this, raw C. We get a class, we call Objective-C get class, the class called NSString. We ask for the alloc selector. We pass that selector to the NSString object, and we get back an ID for a string class. we can then pass, we ask for the init with characters length message, and we pass that message with the variables http pyb.org and 16 in to get the string back. And then we do the same thing with the underlying NS URL. What we get back is, at the end, ID URL, a pointer to a Objective-C object. Okay, so that's raw C. How do we get from that to Python? Well, part of the CPython standard library is a package called ctypes. Ctypes is a library that exploits the fact that the C calling convention is a very well-defined process and can use that to invoke C libraries directly rather than having to write a C module to access functionality in that C library. Using ctypes, all you have to do is reference which library contains the code object you want, then describe the prototype of the method you want to invoke, and you can invoke that method directly. So, taking the standard libc library here, we could load libc, which is the standard C library on POSIX boxes. You can tell that library that the function strchr takes a character pointer and a character and returns a character pointer. So what it's doing is looking for the character D in the string A, B, C, D, E, F, and it will return the string going from that point. Returns D, E, F. That code will run without compiling any binary whatsoever. You don't need a C compiler. It just runs as raw Python code operating over the ctypes layer. So, if you can invoke C libraries directly, that means you can invoke Objective-C directly. Take that very first call to NS string. We can load the Objective-C library, tell that library that Objective-C get class takes a character pointer and returns a generic object pointer. Invoke it. And we get back a pointer to the NSString class that we can then use in subsequent message passing calls. Okay, that's neat, but how does that help? Well, Python is also a very dynamic language, and most aspects of the language at runtime can be configured and overridden, including basic things like attribute access. So if you define a class with a dunder getAttra method, any attempt to access an attribute on that object will be turned into a call to that dunder getAttra method. Similarly, for attempts to set an attribute using dunder setAttra. We can then use that to our advantage. If you've got an Objective-C instance and someone invokes .something on that instance, I can use that as a trigger to do a lookup on an Objective-C API, find a selector that matches, and retrieve an attribute with that selector. Python also allows you to intercept the process of invoking a function. If a class implements the dunder call method, it will be used if someone tries to invoke that object as a function. Again, we can use this as a trigger to invoke an underlying Objective-C method. Lastly, Python gives you the power to control the process of object construction itself. Everyone knows about dunder init, that's the object constructor, but there's also dunder new, which can be used to control the process of instantiating instances itself. We can use this to bind to a specific Objective-C instance or class. Put all that together, and what you get is Rubicon, a library that gives you transparent Python-side access to the entire Objective-C runtime. Any published iOS, or for that matter, OS X or Next Step API is now fair game. Now, I should also point out that Rubicon isn't alone in this space. There is also PyObject-C and PyObjus. However, PyObject-C targets desktop APIs, won't work on mobile without major modification, and PyObjus uses Python, so there is a compiled component. Rubicon is pure Python and sufficiently high level that it will work on both desktop and mobile. Using Rubicon, accessing Objective-C becomes as simple as loading the foundation libraries, getting a representation of the NSURL class, and then invoking a method on it, with the very slight conceit that every colon in a selector is replaced by an underscore. There's no background knowledge of NSURL that's encoded in the Rubicon library here. It's being dynamically generated based upon the fact that we know the name of the class and with the attributes that have been requested. You can even extend Objective-C classes in Python space, declare methods that need to be exposed in the Objective-C environment. You just need to decorate them to let the type construction process know that the method needs to be registered with that Objective-C runtime. This is very useful when you're defining callbacks. But wait a minute, Objective-C, it's an extension of C. C is a typed language, so how do you represent typing information? Well, you use Python 3's type annotations. You'll notice that the poke-with-value method in that slide has an argument value. This is an annotated, an argument v. This is annotated with a type description of int, which the type generation process can then use to drive the registration and say, I'm looking for an integer argument. It also says that it returns none, so it's a void method. But if the callback needs to return a particular type or a particular object class, you can declare that and it will be used. Now, to be clear, this is not a custom language extension or a custom Python extension. This is completely legal Python 3, and it has been since Python 3.0. This is just a slightly off-piste usage of that particular type annotation system. From here, it's just a matter of defining the right classes and invoking the right iOS methods. But you can use any textbook iOS method, or iOS textbook, to guide that process. Stick that code into a cookie-cutter template, and you've got a working, pure Python, completely native iOS app. All that's left is to submit it to the App Store and, well, profit, I guess. So, that's iOS. What about Android? Well, on Android, the native compilation toolchain is Java, although based upon recent US court cases. No, it isn't. It's not the Sun Oracle JVM, though. It's a Java bytecode that is then compiled to system-native format. You can still call system-native code, though. Java provides JNI, the Java native interface, which allows you to call compiled code, compiled C code from within Java. So we can just compile CPython again and link it as an embedded library, right? Well, yes and no. Yes, you can do this. There is a separate roundup ticket, 23,496, tracking a patch for CPython that does exactly this. There is probably a slightly more mature version of that patch with a slightly easier to use toolchain that Xavier de Gaia has a fork that works for Android devices. And this general approach is the way that Kivy actually does provide Android support. However, there is a very big caveat on this. On Android, you can't use the C-types trick because the native libraries aren't exposed as C functions. They're exposed as Java. In order to have native widgets and access native APIs, you need to bridge between CPython and Java using JNI. Now, if you're using a desktop version of Java, and the Oracle Sun Java JVM, that doesn't have any serious constraints. It's fast, it's responsive, and it works really quickly. But on Android, there's a hard limit of 2,000 object references, 2,000 individual JNI references. That's hard-coded into the kernel. And on some devices, it's even lower. It's not something you can find out until all of a sudden you discover your kernel doesn't have enough references. And you need a reference for every data type, every method name, every object instance, every variable that you reference. To start Hello World on Android and fully instantiate all the classes that are involved, you need almost 4,000 references. So you have to do a lot of reference caching and lookup and LRU caching and so on. And that means there's lots of repeated lookups, and it's slow to boot. Slow enough that, to my mind, it probably isn't viable. Kivy does do it that way, but Kivy's approach actually lends it to not having as much JNI interface. Okay, so this is Jython. This is Java, so we can use Jython, right? Well, no, it's not that simple. First off, Jython only hit Python 2.7 support last year, so out of the box, you're missing a whole bunch of stuff. That may not be a major problem, but it's at least worth considering. I'm sure they will eventually get to Python 3 support, it's just not there today. Secondly, Jython actually won't compile for Android. It turns out that Java on Android really isn't Java. The Java standard library on Android, doesn't contain a big chunk of java.nio, all the stuff for dealing with files, directories, and file attributes in a platform-independent way. Strangely enough, Jython needs most of that. It also has a bunch of dependencies, Antler, Xerces, Netty, a bunch of others, and they won't compile on Android. So lastly, what you get with Jython is a fully functioning Python parser and interpreter. This is, as you might expect, not a small piece of code. And unlike a desktop platform, it's code that has to be duplicated on every install because there's no system directory where you can install Python and then have all your applications use that common Python interpreter. Or there is, but it's not a really easy way to use it for native app distribution. Okay, so is there another way to tackle this? Well, yes, there is. Let's take a simple Python function. It sings you a little song. When you run this program, Python parses the code and it compiles it into bytecode. Bytecode is a little, if you haven't come across it before, it's a little bit like high-level assembler. It's a stack-based machine with basic primitives for pushing onto and popping off of a stack. Python even gives you the tools to inspect that bytecode too. The dis module contains a disassemble method that allows you to disassemble any function, any class, any module, whatever, to its bytecode representation. And if you run dis over that sing method, what you get is the raw bytecode instructions. Now, each of these is encoded in the PYC file as in a binary format. This is the human readable interpretation of that code, but hopefully it makes some sort of sense. We configure a loop, setting the bounds of that loop to be line 47 to line 50. We load a global symbol called range. We load 3 constants onto the stack, 100, 0, and -1, and then we call a function. We invoke a function with 3 positional arguments. That's range, 100, 0, -1, and so on. Okay, that's nice, but so what? Well, let's do the same thing in Java. Here's the same code. We compile this with Java-C, and we get a sing.class file. And if we look into that class file, what do we see? You see bytecode. Now, okay, it's different bytecode to Python, but it is stack-based. And there's lots of commonalities. You are loading and storing variables. You're getting symbols, pushing constants, invoking methods. So if they're both bytecode and they're both stack-based, can you convert from one to the other? Yes. Voc is a tool written in Python that can convert Python 3.4 bytecode directly to Java 6 class files. What you end up running, or when you end up running your output class file, it's not a Python code being interpreted. It is indistinguishable from a Java class. And that means you can bridge seamlessly between them. You can reference Python classes in Java and vice versa. There's a couple of very small caveats on that, but for the most part, you just write your Java code, but in Python. So you take your standard textbook API, Android API, render them into Python, compile them to Java, and profit. Here's a snippet of some Android code setting up a main activity. From android.widget import list view. We then define a main activity that extends android.app.activity, and again, that's Python 3 legal syntax. We define an onCreate method that takes self, because it's Python, and a state argument that is an android.os.bundle, and that method returns a void. We invoke super's onCreate method, passing in that state. We then log something, log my app, create new app, and then we create a list view, a new instance of list view. That's all Python code, and it spits out to a class file that you can then run through the whole Android toolchain to dex it and turn it into a runnable binary. So, as with iOS, there's a bunch of Android housekeeping that's needed around the outside of that to actually get it running, and there's a cookie cutter for that too. You run cookie cutter over your template, download the pre-compiled Python Android libraries. It'll even manage compiling the Python code to Java and packaging up as it needs to. Again, full instructions on that GitHub page. Okay, so far, we've been able to write a native iOS application using iOS APIs in Python. We've been able to write a native Android application using Android APIs in Python. Can we do this cross-platform? Can we write our UI code once and have it render on both platforms? Yes. One approach, one I've mentioned a couple of times already, is Kivy. Kivy doesn't use native widgets though. It treats the phone's surface as a canvas on which it can draw, and it draws on that canvas a button. When you place a button on the screen, it's a Kivy button, not an iOS button, not an Android button. So it doesn't look like an Android button, doesn't look like a Kivy button. It doesn't look like an Android button or an iOS button. It looks like Kivy. Now, for me, that's not a satisfactory result. It's okay for applications like games, where the visual style of the game is much more important than platform native behavior. But if you're writing a general consumer app, I'd vastly prefer to be looking at widgets that are consistent with a native platform and acquire all of the accessibility capabilities of that native platform, rather than a lowest common denominator that's native nowhere. And it's not just a matter of taste. Both Android and iOS have all sorts of affordances built in to deal with accessibility issues. Yes, these could be implemented in Kivy, but to the best of my knowledge, they're not. If you use native widgets, you get all that stuff for free. This is where Toga comes in. Toga is a cross-platform widget toolkit that uses system-native widgets. It started on desktop platforms for OS X, Linux, and Windows, but I've been focusing on mobile recently to provide a compelling reason for someone to give a damn about yet another widget toolkit. Toga is a wrapper around system-native calls, so you have a common interface to generating system-native widgets. However, you still have all the access to platform internals if you want. So if you want, you can drop down to a completely native API call whenever you need to. So here's a bit of a taste of what Toga looks like in practice. You define an app that extends the base toga.app class. Startup method even lets you build the app. In this case, we're going to have a list widget. When you swipe to delete an item on the list, we're going to remove an entry. And when we pull down to refresh, we're going to call a refresh method. Startup method also describes a container that's going to hold the list. We set the main window for the app to be that container. The top level container is going to have an action on it, a button up in the top right-hand corner on iOS. When that button is pressed, we want to show a dialog. And the add input dialog has a container that holds an input widget. Now, the bit you can't see here because it's just using system defaults is that the layout of the container is driven by CSS. Or I could, for example, put extra padding around the endpoint if I wanted to bring it in from the screen. The dialog has an accept and a cancel action. When accepted, add entry will be invoked. And lastly, we define some callbacks. When we show the add dialog, we can clear the input as well. When you add an entry, you get the value of the input and add the new list entry with that text and clear it. Remove and refresh follow a similar sort of pattern. And that's it. And if you want to see this running in action, this link is a video to a full version of that app running on iOS, simulator in the movie, but it does work on device as well, and on Android. And for bonus points, almost exactly the same code running as a single-page web application, which means Python code running in the browser utilizing a UI declared entirely in Python. 1 or 1.25 source code bases, 3 apps, all platform native. There's linked to full source code for all those as well, including the native versions that the Toga application is effectively reducing to. The last piece of the puzzle is making it easy to take this generic Python project and turn it into a working iOS or Android project, and that's where Briefcase comes in. I've spoken previously about using Cookie Cutter to generate stub projects. Briefcase is then a setup tools extension that uses Cookie Cutter and the project metadata from setup.py to generate ready-to-compile iOS and Android projects. How do you use it? Well, in your project's virtual environment, install Briefcase, and you say Python setup.py iOS or Python setup.py Android. Then build the same way you normally would. Open the project in Xcode or run an ant build. I'd like to expand this. Also manages the build to do the deploy to device process as well. Other tools have demonstrated this sort of thing is at least possible, so it's really just a matter of putting all the pieces together. And just quietly, Briefcase also works on OS X and Apple's tvOS. I'd like to expand it to Linux. I've had a couple of people ask about whether it could work on Windows, maybe even Apple's watchOS, so lots of possibilities there. Okay, so what does the future hold? Well, there's still a lot of work to be done. I can't speak for Kivy. I'm sure they'll continue to evolve their APIs and platform, and I wish them all the best. I intend to keep working on Rubicon, Voc, and Toga. Collectively, these tools make up what's called the Beeware project. If anything I've said today sounds interesting and you'd like to get involved, I'd appreciate any help. There is plenty to do, and I've got an open offer to mentor anybody who wants to get involved, even if it's your first time contributing to an open source project and you don't think that you've got what it takes to be an open source contributor because you're just a beginner programmer, you don't really know that much yet. Yes, you do. Yes, you know enough. Yes, you can contribute. And as an added bonus, thanks to MaxCDN, anybody who does contribute will receive an exclusive Beeware challenge coin, nice and shiny. I'm here to the end of the sprints, and I'll be working on Voc and Toga. The Beeware was hunkered down in booth 313. Unfortunately, I think we're tearing that down now. So, some people look at what I've been doing for the last 2 years and think that I'm tilting at windmills. And they're at least partially right. But I think that as a language community, we've got a huge threat on our hands. Mobile as a platform is starting to become a really important part of the development landscape. And if Python doesn't have a good story on mobile, we run the risk of being left behind as a language. And that'd make me really sad, because as a community, we've built something really great here. A language that's accessible to newcomers, but robust enough for professionals, useful in multiple domains, with an amazing community spirit. But the threat is also an opportunity. Many of the areas where Python has gained traction, in science, in education, these are areas where mobile has the potential to make a huge impact. Imagine a world where a scientist can knock out, with very little programming experience, can knock out a quick user interface to put in the hands of experimenters to gather information, or provide an app so that citizen scientists can log local flora, fauna, or environmental conditions. Imagine a world where you can get kids excited in programming because they can build something that runs on their phone they can show to their friends. Imagine a Django Girl style event where students leave the tutorial having not just built a blog, but having built a mobile phone app they can use to upload photos and blog entries to that blog. In short, it is the best of times, it is the worst of times. It is the age of wisdom, it is the age of foolishness. It is the epoch of belief, it is the epoch of incredulity. Like a great Dickens novel, the tale of two cell phones is just getting started. If you want to know more, here's my contact details.
Right, we do have a few minutes for questions. If you've got questions, please line up at one of the two microphones here, and if you could please be relatively quiet during the question asking time so that everybody in the audience can hear the questions and the answers. You over here.
Can you offer a few examples of apps that have been built using these processes?
No, I cannot. Unfortunately, like I said, this is very early stages. There is definitely evidence, or like the Apple app submission guidelines have made it clear that this approach is possible, and there are Kiwi apps in the App Store that use the same process that Toga uses. However, this is early stage stuff. I'm really only sort of just pulling this together in the last couple of weeks to be at the point where it's really presentable here. So there's definitely still work to be done. And as a result, I haven't actually pushed a useful application, partially because Apple will reject apps that appear to be trivial. So yes, that's still a work in progress.
Yeah, one over here.
Hi, this is really amazing. I'm blown away. My question is, other languages have done this kind of sort of piggybacking, say on Android, and usually they run into sort of memory issues that are either too big or not fast enough. Can you comment regarding the performance of these apps?
Sure, okay, so on Android, the speed performance is slightly less than if you had written it completely native, because there is, like for example, if you've got a method that takes an integer, it needs to be boxed to turn it into a Python integer so that it can be processed and then unboxed to turn it back into a Java integer. So there is some overhead associated with that. However, it's not huge. You know, it's a manageable sort of level of overhead. And it's also something that with more attention, you actually have enough information in the compilation process to optimize that path. If you know this variable is an integer, that's a float. The only thing you do to it is a multiply, and then you return it. You have the type information to not have to box that and just go straight to the mathematical operation. So in terms of application size, the Toga Hello World app that I showed just there, that's about a 6 meg binary when it actually gets deployed. So it's not a huge runtime when it actually gets deployed to phone. And it's very similar for iOS.
We'll take one more from over here, and then that's all we'll have time for. If you do have questions, you can come up and see Russell afterwards.
So great talk. That was very inspiring.
Thank you.
I have a question to be kind of magic. If it would be possible to compile NumPy on iOS and Android, is that possible?
Haven't looked into it. NumPy, as I understand, does have a lot of C extensions in it. Right. It's at least in the realms of the possible from what I understand. I haven't played with it at great length, so that's all warranty void where not applicable, etc. But you still, you are writing Python code that compiles to a Java class. That Java class could be making JNI calls. So there is at least some potential for that to be done. Exactly how that works, I don't know. Right. Would certainly, if you're hanging around for the sprints, I'd certainly be interested in seeing exactly what that would look like. So,
I'll be at the sprints.
Excellent.
Russell Keith-Magee, everyone.
Thank you.